SubQ-1.1-Small, a long context language model built on Subquadratic Sparse Attention. Let's unpack how it works. We'll start with the problem this work is really about. Not bigger context windows for their own sake, but reasoning over complete artifacts, and why that has stayed expensive. Many of the most valuable AI tasks require reasoning over a complete artifact rather than an excerpt of one. Think of an entire code repository where a single function is defined in one file and called from 40 others. Or a legal contract where a term is qualified on page 2 and amended on page 46. In cases like these, the hard part is not finding the right passage. It is reasoning across relationships scattered throughout the whole artifact. These whole artifact reasoning tasks are precisely where current systems struggle most. The reason whole artifact reasoning stays expensive is structural. Dense attention compares every token with every other token, so its cost grows with the square of the sequence length. Concretely, at 128,000 tokens, that's about 8.6 billion operations per layer. At 1 million, it's 549 billion. And at 2 million, it's 2.2 trillion. Doubling the context roughly quadruples the work. Flash Attention solved the memory side of this elegantly, but the quadratic compute is still there. Because reasoning directly over large artifacts is so costly, most systems work around it. They retrieve, they chunk, they summarize, they orchestrate agents, partitioning information into small pieces and reconstructing it at inference time. Viewed this way, much of the modern AI stack is really scaffolding built around context scarcity. It echoes Sutton's bitter lesson. Hand-engineered machinery that compensates for a model's limits tends to be displaced as learned computation scales. The open question is whether efficient long context could let some of that scaffolding simply dissolve. To see what's new here, it helps to map the landscape of efficient attention and the specific trade-off that has kept these methods from delivering on all fronts at once. Approaches to long context split into two broad camps. Architectural methods change how the model itself processes a sequence, while system-level methods leave the model fixed and orchestrate around its context limit. Within the architectural camp sit several families: sparse attention, latent compression, recurrent and state space models, and hybrids, each cutting cost in a different way. The method in this report belongs here. SSA, short for Subquadratic Sparse Attention, is a learned, content-dependent sparse attention mechanism. The taxonomy places it right beside its closest published relative, DeepSeek's Compressed Sparse Attention, abbreviated CSA. Flash attention is the most important efficiency work of recent years, and it's worth being precise about what it does. Computed naively, attention materializes the full n-by-n score matrix in GPU memory, and memory bandwidth becomes the bottleneck long before compute does. Flash attention never materializes that matrix. It tiles the computation into blocks that fit in on-chip SRAM, keeps running softmax statistics as it goes, and writes only the final output back. Peak memory drops from order n squared to order n, and throughput rises sharply. But notice what does not change. The number of floating point operations is still quadratic. Flash attention solved the memory wall. It did not remove the compute wall that ultimately bounds how far context can scale. Start with dense attention, the standard mechanism. Every token attends to every other token, building a full grid of pairwise scores, so any position can draw on any other purely by content. That all pairs design is exactly what makes attention so capable and so good at retrieval. But it is also why cost grows with the square of the sequence length. Double the number of tokens, and you roughly quadruple the work. At 1 million tokens, that grid of interactions is enormous. Sparse attention asks a simple question: does every token really need to attend to all the others? In practice, only a few earlier tokens usually matter for each query. So instead of the full dense grid, each query keeps just a small, selected subset of keys and ignores the rest. The number of interactions drops from order n squared down to roughly linear, And that is what makes long contexts affordable. The hard part is not being sparse. It is choosing which tokens to keep and choosing them by content rather than by a fixed positional pattern. Recurrent and state space models take a completely different route. Instead of comparing all pairs, they read the sequence one step at a time, folding everything seen so far into a single fixed-size state that is carried forward. That makes them linear by construction, and Mamba, RWKV, and RetNet all work this way. The catch is compression. A fixed-size state can summarize the past, but it cannot store it verbatim, so exact long-range recall, finding one specific fact far back in the sequence, is exactly where these models struggle. Two big families each fail in a different way. Fixed pattern sparse attention computes only some interactions, sliding window or strided patterns. It scales well, but a token attends purely by position, regardless of whether the information it needs is actually there. It sacrifices the content-dependent routing that makes dense attention effective. Recurrent and state space models like Mamba, RWKV, and RetNet take the other route. They abandon all pairs comparison and carry a compressed state forward, which is linear by construction. But a fixed-size state is lossy compression. It can't reproduce earlier tokens verbatim, and long context retrieval needs exactly that. Before going further, one idea deserves a gentle introduction: content-dependent routing. Routing simply means deciding which earlier tokens a query is allowed to look at. A fixed pattern routes by position. For example, always attend to your nearest neighbors, regardless of whether anything useful is actually there. Content-dependent routing decides by meaning instead. The query looks at the tokens that are genuinely relevant to it, wherever they happen to sit in the sequence. That flexibility is what lets a model reach far back and pull out the one fact that matters. And it is exactly the property the next approaches are trying to preserve while staying efficient. Closely related is retrieval from arbitrary positions. In a long context, the fact you need be anywhere, 3 tokens back, or 3 million tokens back. A useful long context model has to reach any of those positions with equal ease. This is where many efficient designs quietly fail. Sliding window attention can only see a fixed recent span, so anything older is simply out of reach. A recurrent state has technically seen the whole past, but it is compressed, so a specific distant detail may no longer be recoverable. Retrieving precisely from arbitrary positions, near or far, is the capability that long context reasoning actually depends on. The promising middle path is learned sparse attention. DeepSeek's native and compressed sparse attention use a lightning indexer, a learned mechanism that scores which positions each query should attend to. That restores the content-dependent routing fixed patterns throwaway. But there's a catch the report highlights. The indexer is itself a full attention transformer, so the act of choosing where to attend is quadratic. Past about 50,000 tokens, it overtakes the very attention it feeds, roughly 16 times more costly at 1 million tokens, and 190 times at 12 million. The cost just moves into the selector. Putting it together, a complete long-context solution needs 4 properties simultaneously: subquadratic scaling, content-dependent routing, retrieval from arbitrary positions, and production-grade maturity. The recurring pattern is that every prior family meets some of these, but relaxes at least one. Dense attention is content-aware but quadratic. Fixed pattern, sparse scales but loses routing. Recurrent models scale but can't recall precisely. SSA is the attempt to satisfy all 4 at once. So how does SSA do it, and how was the model actually built? This is the core of the work. SSA was designed around 3 requirements held together. First, dense attention level quality. Routing must be content-dependent, decided by the tokens themselves rather than by a fixed positional pattern, so the model can retrieve from arbitrary positions. Second, subquadratic scaling. Each query attends to a small, selected subset of positions, and the selection, Retrieval and attention steps are each linear in sequence length, so the whole mechanism is linear end to end. Third, full context training with standard autoregressive generation. The model optimizes over the entire context during training while still decoding token by token at inference. The key idea is that the selection itself is sparse and linear. Unlike a lightning indexer, SSA never pays a quadratic price to decide where to look. SubQ-1.1-Small wasn't trained from scratch. The team took an existing open-weight frontier model and converted it, replacing its dense attention with SSA. Long context capability was then developed through staged context extension and large-scale continued pre-training that emphasized naturally long data, books, long documents, and repository-scale code. A central challenge was capability balance. Long context training can quietly erode reasoning and knowledge, so targeted post-training was designed to optimize many capabilities at once rather than retrieval in isolation. First, what is a donor model? Training a capable language model from scratch is enormously expensive, so SubQ-1.1-Small did not start from zero. It began from an existing open-weight frontier model, one that was already fluent and already strong at reasoning and code, and borrowed its weights as a starting point. That pre-trained model is the donor. The team then performed a kind of transplant. They kept the donor's knowledge, but replaced its dense attention with subquadratic sparse attention. Starting from a strong donor means all the later work can focus on one thing, long context, instead of relearning language from scratch. Now, let's gently introduce Yaren. The idea starts with how a transformer handles position. It does not read positions as plain counts. Instead, it encodes each token's place using rotating signals, and it only ever learns the range of positions it actually saw during training, say up to around 260,000 tokens. Push it past that range, and those positional signals fall outside everything the model knows, so quality collapses. Yaren is a rescaling trick. It gently stretches and adjusts those positional frequencies so that a much longer sequence maps back into the range the model already understands. With Yaren, the context window can be extended to a much longer length with only light retraining, instead of breaking at the boundary. Context length wasn't extended in one jump. The donor model supported a 262,000 token window. Using Yaren to rescale the positional representation, the team extended in stages to 512,000, then 1 million, then 2 million tokens, with long context continued pre-training performed between each extension rather than directly at the final length. The vast majority of pre-training tokens were seen at the 1 million token stage. Crucially, because SSA made iteration cheap, under a minute per step at million token context, they could run more than 100 long context experiments and actually search for a training recipe, rather than guess at one. Now, what all of that produced, across retrieval, knowledge, coding, agentic tasks, and efficiency. The headline result is that long context retrieval generalized far beyond the training window. On Ruler, NVIDIA's 13-task context benchmark, SubQ-1.1-Small reaches 99.12 at 128,000 tokens. Single needle retrieval is perfect, 100%, all the way through 2 million tokens, and it still holds 98% at 6 and 12 million, roughly an order of magnitude beyond its primary training window. And it does this while attending to only 0.13% of token pairs at 12 million tokens, close to a 1,000-fold reduction. Retrieval behaved like a learned capability, not a fixed-length specialization. A long-context model that retrieves precisely but reasons poorly hasn't solved much, so knowledge and coding matter as a check. On GPQA Diamond, a graduate-level science benchmark, SubQ-1.1-Small scores 85.4, landing between the small and mid-frontier tiers, ahead of the smallest models and close to mid-sized ones. On LiveCodeBench, it reaches 89.7, ahead of Sonnet 4.6 and GPT 5.4. The takeaway is that optimizing for long context did not come at the expense of reasoning or coding. The capability balancing post-training preserved them. Beyond retrieval and knowledge, the team tested long-horizon agentic work with AutomationBench Finance, realistic business tasks that orchestrate actions across about 500 APIs in 47 applications, graded only on whether the right data reach the right systems, with no partial credit. SubQ-1.1-Small reaches 13%, close to the absolute frontier. Opus 4.8 at 16 and GPT 5.5 at 18, and well ahead of Sonnet 4.6 and Haiku 4.5. That's early evidence that the same long-context training regime transfers to sustained, multi-step reasoning. All of this rests on the efficiency win, and it's worth stating precisely. Dense attention costs on the order of n squared, SSA costs on the order of n. That changes the curve, not just the constant. Measured on a B200, SSA reduces attention FLOPs by 64.5 times at a 1 million token context. Against Flash Attention 2 on a single layer, SSA reaches parity near 16,000 tokens and pulls away to 56 times faster at 1 million, running in under a second where Flash Attention 2 takes 54. This is not a fixed speedup, it's a scaling law advantage that grows more valuable as sequences get longer. Two implications close the story. First, efficient attention changes the development loop itself. When long-context experiments are cheap, teams can search for a recipe instead of guessing, and long-context continued pre-training turned out to be the most consistent lever for retrieval gains. Second, for deployment, as reasoning over complete artifacts becomes cheap and reliable, some of the retrieval, re-ranking, and orchestration that exists to reconstruct context can move into the model. The point isn't bigger windows for their own sake. It's models that reason over whole repositories, document collections, and knowledge bases directly, with less chunking and less scaffolding around them.
If you like this video, please subscribe and share. Thank you.